My name is Dave Short. I think I have some insights about grid scale power and water production using renewables that others may not have explored fully. I hope you find this presentation useful. California has successfully encouraged huge amounts of solar panel installations, making more daylight solar energy production than the grid needs or can use. Often about 5% gets wasted. So rooftop solar energy is becoming less and less valued, while the energy produced to meet the evening peak demand is more and more valuable. The most cost-effective and the most reliable method of grid-scale energy storage that can handle the peak demand is pumped hydroelectric power generation. But because of long-term drought, the water in dozens of large pumped hydro storage dams is shrinking, and the amount of reliable energy being stored has become less and less. The 8 states in the lower Colorado River Basin have been enduring a mega drought for the last 23 years. It is likely that the available river water will continue to decrease. This August, the Department of the Interior has had to mandate large and significant water use restrictions for many states. California and Arizona are being particularly hard hit. So why not use daylight solar energy to desalinate seawater? The seawater would be used as feed water for a pumped hydro storage facility, which, in turn, desalinates seawater 24 hours a day using renewable energy, not using fossil fuels. There is an unusual and undeveloped site along the Southern California coast very close to the nuclear power plant at San Onofre. The nuclear generation station was deemed too hazardous to continue operating about 10 years ago. Energy storage using pumped hydro requires an upper reservoir to hold the potential energy and a lower reservoir where energy is generated and pumped using water turbines. If 1 cubic meter is elevated to 370 meters, it has or requires about 1 kilowatt hour of energy. One can expect about a 22% loss of energy round trip. Existing contour elevations of the top of San Onofre Bluffs indicate that with standard grading, a reservoir over 2 square kilometers can be created. The water in the upper reservoir would be at least 400 meters above sea level. If the reservoirs have embankments about 10 meters high, a volume of water with the potential to produce 20 million kilowatt hours might be created. 6 million kilowatt hours might be expended in a typical evening's operation of the turbines in a 2 gigawatt power plant. There are several important benefits gained by making a seawall parallel to San Onofre Beach. The resulting San Onofre Lagoon would have well-controlled water flows of already once filtered water in and out powered by the tides. The pumped hydro would have a lower reservoir at sea level to maximize the potential for energy production. The Coastal Commission and the State Lands Commission and several environmental organizations have had reasonable objections to the seawater desalination. The process releases many tons of carbon dioxide to get the energy for pressurized reverse osmosis. There has also been a risk to sea life from the discharge of salty brine and the initial filtration methods. The Poseidon desalination plant at Carlsbad, California, has been producing about 50 million gallons per day at half a cent per gallon for about 6 years now. To produce that 150 acre feet of drinking water per day, it used a dedicated 30 megawatt fossil fuel plant to supply the energy. About 4,600 kilowatt hours of energy is needed to produce 1 acre foot of desalinated water. A kilowatt hour of energy made with fossil fuel typically sends about 9/10 of a pound of carbon dioxide into the air. So, 1 acre foot of drinking water also creates about 4,000 pounds of carbon dioxide. A reasonable concern from environmental groups is that when Poseidon produces the 56,000 acre feet of water each year, the energy required for the reverse osmosis has also released over 200 million pounds of greenhouse gas into the air for that year. This drawing illustrates how the proposed seawall creates San Onofre Lagoon and the lower desalinated water reservoir. It also shows how the pumped hydroelectric power plant and the reverse osmosis desalination plant could be oriented. The energy of the tides can be utilized to power the filtration of ocean water, leaving material bigger than 1 millimeter in the ocean, and then to backflush the filtration systems efficiently before the clean, salty water is sent onshore to the desalination plant. Seawater needs to be filtered several times and in several ways before it gets to the salt ion removal stage. The seawall facilitates several filtrations down to about 70 microns before it would get sent on shore for the last filtration and the ultimate salt removal. All sea organisms and material larger than the head of a pin, a millimeter, would be left in the ocean with the initial filtration. The second stage of seawater filtration can benefit from a number of multimedia filtration stations sited at the lagoon side of the seawall. Water allowed into each filtration station would have been screened to remove material between 1,000 microns and about 300 microns, with that material easily routed back to the ocean side. The water with materials 300 microns or less would then be pumped to the top of anthracite, sand, gravel filtration systems. Water coming out of the bottom should be cleaned to about 70 microns and ready to send onshore for final filtration and salt ion removal by reverse osmosis. The multimedia filtration systems typically are backflushed with air and water every day or two. With the multimedia systems at the seawall, the backflush water and microscopic sea life can simply be routed back into the ocean where it came from.